Okay, let's talk about increasing, decreasing, or constant parts of a graph. What that means, or how that we find those parts of a graph. So let me put a function up here so we can talk about it. All right, so this is just kind of a parabola, I mean, x squared graph, but we'll talk a lot more about that later. But don't even need to know what that particular function equation-wise is. A function is increasing. It's really fairly simple if you have the graph to look at, which I put one up here. That's a positive one, by the way. A function is increasing if it's rising from left to right. Rising from left to right makes sense because look, from left to right here on this starting at 1 there. Yeah, if we're going left to right, the motion is upwards, so it makes sense that would be considered increasing. The visual of it makes sense there. Yeah, this part of the graph is increasing. Guess what? The function is decreasing if it's not rising. It's decreasing if it's going downwards. If it falls, I guess. Just said that easier, but so a function, oh my word. Function is decreasing if it is going down from left to right. Like this one is here. So yeah, you look at the progression here from left to right, down, down, down. So yeah, this part over here is decreasing. So it makes sense. Visual makes it make sense. Now, why is that? Just a little, let me explain that a little bit. Why is we say increasing and decreasing for that other than the visual there? Well, it has to do with the function value if you think about it. So on this increasing part here, it's vice versa for the decreasing, but if you look at from point 1 to point 2 here, if you think about the function values for those particular points, so we've got this function values over here, and then as we go along, the next function value is over here. So the function value went from here to here, didn't it? The y value, that's increasing. Over here on the other side, if you go from one point to this point where it's decreasing, look at that. This function value is up here, and then the next one I've got marked there is up here. So that's going from this function value down to that function. That's decreasing function values. So that's why it is, and there's, I think it may put it in notation for it in the book there. But it's because the function values, the f of x's are growing or they're falling. So anyway, now, again, like with domain and range, we're going to use interval notation. Use the interval notation for the increasing part and the decreasing part. Use the domain intervals, x intervals in other words, okay? Instead of the y intervals, you're going to use the x intervals. And so, yeah, that's why I marked this one. We got x is 1 is kind of the dividing spot there. And so it's increasing from 1 and beyond. So that'd be 1 to infinity. And then it's decreasing on the other side of 1. one back. Well, that's negative infinity is the left hand endpoint there. There's not a left hand endpoint, so we call that negative infinity. Negative infinity to 1. And by the way, it also says in the book, or you might see it there, it talks about open intervals. Open intervals just mean you're not including the endpoints. So that's all that means. These are open intervals. The endpoints are not included. Anyway, is that good? Makes sense? Okay, what about this one? Where is this one increasing? Where is this one decreasing? -2 is going to be a mark, and then 3. Translate this to your paper here. I'm going to hit that point, and then I'm going to hit a point below 3 there. Up and down. So where is that one increasing and decreasing? Well, like I said, it's easy on the graph to see this because you just go from left to right. If you follow along, you're going up, down, up. So the up parts are increasing, down parts are decreasing, and the up parts are decreasing. So I've got 2 increasing, and then 1 in the middle is decreasing. So how would I write that? Well, again, that's why I specified those x values there. It's increasing, well, it's headed downwards there infinitely, but it's increasing from negative infinity to the -2, the top point there. Oops, said it right, but I wrote it wrong. Negative infinity to -2. Then it goes to decreasing from -2 to 3, right? In here it's decreasing. And then it turns back around at 3 and goes back to increasing. So 3 to infinity for that last part. And then like I said, if you got 2 of those interval notations together, they usually throw the union sign between them. So, good? All right. So let's do this one, because I haven't talked about one of those things up there that I said we were. All right, so this graph, let's see if I can draw it up here. So this one's going to be, something happened there at -1 and then 4. All right, so it goes up to -1, and then it flattens out all the way to 4. It goes back, goes back up. So it kind of got those corners at -1 and 4. All right, so where is this one increasing, first of all? Well, the up parts are this part, and then this part over here is also increasing. So we've got, again, like I had over there, 2 increasing parts. So it's all the way back here as far as the x's go. So negative infinity to -1, increasing. And then starting at 4 to infinity. So they use open intervals. That just means you're not including the endpoints, not doing the square brackets there. Where's it decreasing? Well, in here it's flat, or I meant for it to be flat. Is that decreasing? No. It's not going downwards. No intervals of decrease there. But I do have that flat part. Well, the flat part, it's neither increasing nor, it's not going up or down. So guess what? That's constant. Yeah, the constant is when you have those flat parts in your graph. If you've got a flat part, a horizontal part, however you want to say it, those are your constant parts of your graph or function. Um, it's a more technical term, would be horizontal. Yeah, the horizontal parts and flat parts, those are your constant parts. So this one's constant between the -1 and 4. It's not increasing or decreasing, it's constant. Yes? All right. Okay. All right. So let me talk about a couple other things here. Any questions about increasing, decreasing, or constant? Everybody got that one? I was killing time there. All right. Let's talk about relative maxes and mins, relative maximums and relative minimums. And I'll draw this up here, but I do have a handout for you all here. All right, so the first one goes, all right, so what am I hitting there? -3, that's going to be a good one to mark, and then 2, okay, so it's crosses there about -4, it's down, down, and then -3 kind of turns around, goes up between -1 and 2, all the way to 7 here, y, and then down somewhere along in here. All right. Yeah, so we'll call this point down here where it turns around as y value -9, and then what it looks like it's between 1 and 2, doesn't it? Between 1 and 2 is that point there, because those are the ones we're going to focus on. Yeah, it turns out a relative maximum, what that means, call it relative max, what that means is a value, a high point. A relative maximum is at a high point. So in this particular case, I've got a relative maximum at 0.7 for this particular function. 0.7, that's a relative maximum. A high point is where a relative maximum occurs at 0.7. And the reason is, the reason it's said to be a relative maximum, it's a maximum relative to the other points around it. If you want to know why, I guess the name is what it is. It's not necessarily a maximum for the whole entire function, but for the points around it, it's a maximum, isn't it? Just look at the points around it. Up, up, down, down. So that point is the highest point around it. So it's a maximum in that regard. Okay? That's all really that term is meaning. It's the largest one around in the neighborhood of that particular point. Okay? And so you might also see the term local max or min. also called a local max or min. Local max. We'll talk about the local min in a second. Different ways to write it. So in this particular, I think that's the way you may see the answer provided. At 0.7 is our relative maximum. To be honest though, what's maximum about it? It's the function value. So a better way, maybe a more precise way of saying it, or a better way, yeah. F of 0 equals 7 is our relative maximum. Usually input the function notation kind of thing, calling this function F. If that's the function name. Because it's actually the function value that's the maximum. It's the F at 0, and the 7 is the actual value there. And we could say got a relative max of 7 at x equals 0. So, anyway. Guess what? Relative min, on the other hand, guess what it is? A low point, considered of those around it. Low point of the graph is considered a relative min, and so what do we got here? So, yeah, this -3, -9, so I've got a relative min at -3, -9. But there's also another one here at the 2, and it's, I believe it's 1.5, we'll call it. Oh, positive. Or however we need to phrase it. Okay, so those are relative mins. They're, if you look at it, it's a minimum compared to the points around it. There's a lowest point there, and that's actually the lowest point on the graph, but over here, there's lower points than that one, right? But it's the lowest point around, so you have a relative min at those low points. That's the way we call it. Okay, so that's maybe not necessarily a definition, but that's what they mean when we have the graph. Local, also called local min. You may see that too. All right, any questions about that? So looking at that second one then, I do this one because the second one is a little bit trickier, kind of the location of the maxes and mins. So this one just goes down, kind of turns around between, I got 0 and -2 there. It comes up right on the other side of +2, goes up somewhere seemingly like that, and then comes back down about that 6 on the other side of 6. So yeah, it's a little not as precise location as maybe those other ones, and that's so. What they'll have you do here is, let's just approximate the relative maxes and mins on that one. That's what we'll do there. Okay? Approximate the relative maxes and mins. So, yeah, I mean, we can get more precise with some other mathematics, but for our purposes, yeah, let's just approximate them. We know the low points, so we've got a relative min at those, so we've got a relative min in this area here. So that's going to be a relative min at, let's say, I believe it's how they'll, one way to give it. So yeah, it's between 0 and -2, I clearly see that. Do we want to call it -1? Could be. My markings don't have it -1 on there, but it looks like it. So yeah, it's an approximation. So let's just call it -1, -18. Yep. Okay with that? This point here is close enough. I think we can call it -18. Well, the high point, those are relative maximums, so we're going to call the relative max. What are you going to say there? Did we put their answer down yet? Well, it does look like it's close to 4, but I'm thinking it's not quite 4, and maybe not even 5, so I'm going to call it 4.5, but it's an approximation, so if you get in the ballpark on these, should be okay. All right. So that was my point of doing this one is, you know, if you're close on these, since we don't have other ways of doing this, we're just eyeballing it in. So 4.5, and then the y value for that point. I don't think it's quite 9, is it? To me, it looks like it's right above the 8, but not quite 9. So let's call it 8.5. That's what I'm gonna call it. But they're approximations. Okay, so if you're in that closeness there, close to those, we should be fine. Sometimes we like the preciseness, but these are approximations, okay? Any questions about that? So I got one more thing to show you. All right. Good? Okay. Average rate of change. Average rate of change. The definition, I guess we'll go with that. The definition of the average rate of change, it's just a name given between the slope of a line between 2 points of a function. So we can think of the average rate of change as the slope of the line between 2 points on a graph of a function. So we know about slope, so we can figure that out, but that's also termed, what is termed as the average rate of change, and I'll show you examples as to why maybe that is the case, why it's called that, but anyway, the slope of a line between 2 points on the graph of a function, average rate of change, from, or between those 2 points. Let me phrase it a little different. Okay, so let's just take any old function here. Doesn't really matter what the graph looks like. Let's just say it goes down, up, down. Okay? So, average rate of change from this point all the way over to this point. The slope of that line between those 2 points is the average rate of change for that function from or between those points, okay? I'll phrase it a little different maybe when I do actually write this out. All right, so how do we calculate the average rate of change? It's a slope. You're just going to do a slope. How do we do the slope? Difference of the y's over difference of the x's, right? Well, let's say this is f of x, so yeah, so kind of give it a name here to these points. So let's call this one x1, this x2. Those are just the x values for those points. If I want to write an ordered pair for each one of those, this point right here, the x is x1, the y is whatever y you get from the function. So it'll be f of x1 And over here, x2, comma, f of x2. Those are the x ways we could write xy for those two. So your average rate of change is just the slope between those 2 points. That's what the formula looks like. So this is a way maybe more precisely say the average rate of change of f from x1 to x2, where's the x values go, equals, and that's what I was saying, it's the slope of that line. So it's not a line, the function's not a line, but this average rate of change is it's a slope of a line. So you're just going to calculate that slope. F of x, oops, difference of the y's over difference of the x's. Slope. Called the average rate of change, though, if we put it in those terms. All right, so let's do a couple and wrap this thing up here. Okay. All right, so find the average rate of change for f of x equals 3x squared minus x cubed from x equals 1 to x equals 4. Average rate of change for this function from x1 to x4. So the average rate of change is equal to, this is slope, difference of the y's over difference of the x's, but in function notation be f of the x2, the second x, minus f of the first x, divided by just the difference of the x's. And so in this case, first x and second x, 4 and 1. So I'm just going to calculate, they don't give us the function values, but it's f of the x2, f of 4, minus f of the x1 over x2 minus x1. So yeah, just have to calculate the y values and then calculate your slope there. It's really just a slope type problem, but that's in the context of this problem. It's also known as the average rate of change. I'll show you why that might be in a second. Okay, anyway. All right, so what is f of 4? F of 4 here, we'll do it over here. F of 4, just going to plug in 4, so you got 3 times 4 squared minus 4 cubed. That's 3 times 16 minus 64. 48 minus 64, negative 16. Is that right? That's the hardest one. Did I do that right? Negative 16? Let me know if that's right. All right. F of 1, all right, so f of 1, that's a lot easier. 3 times 1 squared minus 1 cubed, that's 3 minus 1, that's 2. So negative 16 minus 2 is on top, and of course 3 on the bottom, so I'm getting, oh, really nice. Don't always work out that nicely, but I'm seeing negative 6. The average rate of change from x is 1 to x is 4 is negative 6. Negative 6. And, all right, so the idea behind this, the average rate of change, why that is, let's see if this kind of helps it make sense there. But is that okay? Is that right? I'd like for that to be right, if that's right. If it's not right, I'd like to change it. Good? Good. All right, thank you. Okay. So one more of those. Okay, let's do it here. Kind of an application to kind of maybe see why it is called the average rate of change. All right, f of x equals 0.2x squared minus 1.3x plus 24. And that represents the temperature from 8 a.m. to 12 p.m. Where x equals 0 is 8 a.m. All right, so it gives me the temperature if I plug in the time where x is 0 represents 8 a.m. All right. Okay, so here's what I want to do. Find and interpret the average rate of change for F, for the temperature, from 8 to 12, okay? AM. 8 a.m. to 12 p.m. Average rate of change for that. So we just talked about the average rate of change, the way we calculate it. Let's come over here. Let's have a little bit of room to write. So it's calculated. You take f of x2 minus f, it's the slope formula, but using the function notation, over x2 minus x1. All right. So what have I got here? As far as the x's go, so the x's are the times, right? So 8 a.m. would be my x1, and 12 p.m. would be my x2. But that's also with the conversion here. We know that x equals 0 is 8 a.m., so what would that make x2? 12 p.m. 4? It's 4 hours from 8 a.m. So my x2 and x1 are 0 and 4. That's the first thing to understand there. Everybody good with that? 4 to 0? Or 0 to 4, I guess. Better way to put that. And so in this case, I need to do f of the x2, 4, minus f of the x1, 0, over x2, 4, minus 0. The x's, difference of the x's is what the bottom is. Okay? Sound all right? Okay. So again, the top, we do have to calculate those. It's the function values at those x values. So plug in your x to be 4.2 x squared. So it'll be 0.2 times 4 squared minus 1.3 times 4 minus, plus 24. So that's 0.2 times 16 minus 1.3 times 4. My calculator is saying plus 24. That's 22. It's 22. F of 4 is 22. F of 0 is a little easier. Plug in x to be 0, 0, 0, 24. And then 4 minus 0, that's 4, so I've got a negative. Negative 2 over 4, so that's a negative 1 half. Negative 0.5. Yeah, since that's in decimal, let's change it to decimal. Negative 0.5, that's my average rate of change for this particular case, negative 0.5. Now, the interpret, that's why I wanted to say, it's kind of why this is called the average rate of change. So if you look at it from the perspective of what are the units here of my average rate of change? Well, what are the units of that thing? Well, it goes back to how we computed that. The units of it, so we've got on top the F values, and on the bottom we got the X values. So what are the function values in this case? So the top units would be, what are the units? So it would be the units of F, typically this, over the units of X. Wouldn't that be the units of my average rate of change? Does that make sense? The units of F are the top, the units of X are on the bottom. That's the units of the average rate of change. So what are the units of F here? F is the temperature, I didn't say, but no surprises there. I guess I should have put that. The temperature is in degrees Fahrenheit. I think. It could be Celsius, I guess, but we'll go with Fahrenheit. Okay, so these are in degrees. Degrees Fahrenheit. The temperature is in degrees Fahrenheit. So that's the units of F. Degrees Fahrenheit over the units of X. Well, X is time. These are hours.